الفيديو التالي يوضح أمثلة مختلفة عن ال solubility product constant ال KSB وعلاقتها مع المولر solubility، وكذلك أمثلة مختلفة لأملاح شحيحة الذوبان. أتمنى لكم التوفيق والنجاح في أمان الله.
Each raised to the power of their stoichiometric coefficients, which in this case is simply 1 and 1. Notice that we do not include the solid itself in this expression, as we do not include solids in equilibrium expressions. The smaller the constant, the fewer the ions that will be present in solution, and therefore the less soluble the substance must be. And compounds that are extremely water insoluble will have KSP values on the order of 10 to the negative 30, negative 50, or even smaller. Let's make sure we can write these solubility products for various equilibria. Take something like calcium carbonate. First, we must write out the complete equilibrium. Upon dissociating, this will form a calcium ion and a carbonate ion. Therefore, the solubility product will be equal to the product of these two ion concentrations. If we have something like magnesium hydroxide, it's the same thing, except that dissociation produces one magnesium ion and two hydroxide ions, which means that hydroxide ion concentration will be squared in the solubility product expression. We can even do this for something more complicated, like apatite, which is a mineral. This will dissociate into 5 calcium ions, 3 phosphate ions, and a hydroxide ion. So the solubility product expression will look like this. In this way, a number of ionic compounds that we previously deemed insoluble should actually be categorized as slightly soluble. If we have a way of measuring ion concentrations in solution, we can calculate the KSP value for a given substance. Let's say we have a saturated solution of milk of magnesia, which is magnesium hydroxide. This is slightly soluble and dissolves according to the following equilibrium. Say we measure the resulting magnesium ion concentration as being 3.7 times 10 to the negative 5 molar. What will be the solubility product for magnesium hydroxide? First, let's write the KSP expression for this substance, which we derived earlier. Notice that hydroxide concentration is squared due to the coefficient in the equilibrium. Now, if this is the concentration of the magnesium ion, then the hydroxide ion concentration must be precisely double, since there are 2 hydroxide ions for every magnesium ion in this substance. So all we need to do is plug these 2 concentrations into the expression, evaluate, and we will get 2.0 times 10 to the negative 13 for KSP, which will be a unitless constant, just like other equilibrium constants. We can also go the other way around and predict the concentrations of ions that will result in solution when dissolving a substance with a given KSP. Let's say we place copper 1 bromide, which has a KSP of 6.3 times 10 to the negative 9, in aqueous solution, which will then generate copper ions and bromide ions to some extent. What will be the molar solubility of this substance, meaning how many moles per liter of the formula unit will dissolve? To find this, we can write the solubility product expression and use this to construct a simple ice chart. In this, we will not list any values for copper bromide, as this is a solid. The ions themselves will start at 0. The change will be x because of the 1 to 1 to 1 ratio, and this means that the equilibrium concentrations of the ions will also be equal to x. Therefore, the KSP will be equal to x squared, and x will be 7.9 times 10 to the negative 5 moles per liter. This is the molar solubility of copper 1 bromide, which in this case is simply the concentration of copper ions and bromide ions in solution at equilibrium. This can be a little trickier if the KSP equation involves exponents, but the process is essentially the same. Let's look at calcium hydroxide, which has a KSP of 8.0 times 10 to the negative 6. Say we place this in aqueous solution, which will produce some calcium ions and hydroxide ions. Again, let's write the KSP expression, noticing that the hydroxide concentration must be squared, as there will be 2 hydroxide ions for every formula unit of calcium hydroxide that dissolves. Then, when we make the ice chart, we will notice that again the initial concentration of each ion will be 0, but the change will be x and 2x respectively due to the stoichiometry of the equation, and the equilibrium concentrations will also be x and 2x. Putting these into the KSP expression, we get that the KSP will be equal to 4x cubed. Now solving for x, we divide by 4 and then take the cube root, leaving us with 1.3 times 10 to the negative 2 for x, which will therefore be the molar solubility, which we can interpret as the solubility of the solid expressed in moles per liter, or the moles of the solid that will dissolve per liter of water. So now that we've learned a bit about the solubility product, it's time to learn a few applications of this concept. But first, let's check comprehension.